Welcome back to Physics Fundamentals. In this video, we're going to be talking about work and power. We'll start off with work. And one of the big issues that we come across in this lesson is these ideas, work and power, are things that are used in everyday English language. And unfortunately, the meaning in physics and the meaning in everyday language don't line up with each other very well. For most people, when you hear the word work, the first thing you think about is a job. And by and large, that is not what we want to talk about here. If you're not thinking about a job, you might be thinking about something a little bit more abstract in the same sense, right? Labor, or maybe even effort. Again, not really what we're going to be looking at. The key idea that I want to think about with work is the result. Work in physics is done by one object and to another object. Right? That's not a very exciting definition. That's not quite the entire definition, but it is a place to start. When we are thinking about work, we have to think about two things. And for the early examples, I'm going to think about me or you or another person as the object doing the work, and then some inanimate box of some sort as the object having work done to it. Work is the result of a force being applied over a distance. So if you are pushing on a box and the box slides across the room, you are doing work by moving the box. If you are pushing on the wall, well, the wall isn't going anywhere. You're putting effort into pushing on the wall, but you get no result. You don't move. There's no distance over which you are pushing. You just stay in place and push on the wall and exhaust yourself without doing anything. Right, so that's the idea that I was talking about up here when I said that work is going to be a result, not an effort. Mathematically, we say that work is force multiplied by distance. And as you look at that formula, you might get to be a little bit confused thinking about the things we've been talking about recently. Force and distance are both vector quantities. And it turns out that thinking about them as vectors actually makes it harder to deal with work. So we want our force and our distance to be in the same direction. And I'll come back to this formula quite a bit later on in the lesson. But to be formal about it, we want to take the magnitude of the force, multiply it by the magnitude of the vector distance, or the vector displacement, and then multiply those by the cosine of the angle between them. That will give me the component of the force in the direction of distance. Again, we'll come back to that a little bit later, but I didn't want to go even into the first example without acknowledging that we do have to think about direction. if the force is pushing in the direction that the object is moving, then we don't have to think about it. And that makes life a lot easier. So jumping into our first example, a mover must overcome 225 newtons of friction as she slides a dresser down a hallway at constant speed. And apologies, I left a little bit out of that. We need to know specifically that she is sliding this dresser a distance of 22 meters down the hallway at constant speed. And I didn't put the question here, but how much work does this mover do? Well, setting this up is relatively straightforward. We are asked about work. We have one formula for work. Work is force times distance. We're given the force. Well, we're almost given the force. We are given that the force of friction is 225 newtons. The force of friction would oppose sliding down the hallway. So this worker must put the same 225 newtons into pushing the dresser down the hallway. And because we want the dresser to go at constant speed, those forces are going to be in equilibrium, the force being applied by the mover and the force of friction slowing it down are going to be equal in magnitude, but in opposite direction. I'm not going to write down any equations to talk about that, but that is reasoning that I have to go through. Right? The force of friction is opposing motion. The worker needs to put in the exact same amount of force in order to get this to move at constant speed. And since friction directly opposes motion, then the force applied has to be directly with motion at 225 newtons. If the force is being applied at some weird angle, well, then there has to still be 225 newtons of force in the direction of motion, and the rest of the force is wasted effort. All right. So, a long way to go to say we can just write down the force that was given to us. The distance is given to us, and there is no real argument to talk about there. The distance is 22 meters. So we can plug those things into our formula. We can grab out our calculator, and my calculator tells me that this comes out at 4,950 Newton meters. Right, now we come to the second challenge of this lesson. Although I guess as I'm looking at this, I only have two significant digits here, so I should have rounded that. And instead of calling it 4,950, I should have called it 5,000, with that first zero being significant. All right. So, because the ideas of energy have been so well used, we decided to give them their own name. So the Newton meter is the same thing as the joule. I have it written down here somewhere. Joule's first name was, I believe, James. Yes, James Joule is, or was, an English physicist who worked in the mid to late 1800s studying the ideas of heat. And he is being recognized. The unit of energy is named after him. We are going to end up with a bit of an alphabet soup of units by the end of this course. Right? And it's all just a matter of hiding things, right? The joule is the same thing as the Newton meter. And of course, the Newton itself was hiding things. A Newton is a kilogram meter per second squared. So a joule is a kilogram meter squared per second squared. We could write it like that every time. But I think you're already starting to see how ugly and complicated these units can be. And so for the sake of making life easier on ourselves, we use these shorthand conventions. But this is something that's generally worth having in your back pocket, right? Having on a reference sheet. Remember how all of the units relate to each other, because we're going to do things like take a joule divided by a meter and get a Newton, or take a joule and divide by a kilogram and then take a square root and get a meter per second. These are just going to be things that come up, and it's a real easy place to get lost and feel like there's just black magic happening, when in reality it's just definitions. So this is a definition that is worth having at your reference. So that's the basic idea of work. The other thing I said I was going to talk about in this video is power. And again, colloquially in English language, when we say the word power, a lot of people think about electricity. And while electricity certainly is an application of power, the idea of power is far more broad than just that. Another common misconception is people think of power as strength, sometimes in a physical sense, right, muscle mass, sometimes in a metaphorical sense, right? The President of the United States is a powerful person because they are in a position of power. But again, not at all the kind of power we want to talk about in a physics course. In fact, our idea of power is going to be related to speed. Power is the rate at which work is done. So to calculate the amount of power, you are going to take the amount of work and divide by the time it takes to do that work. Right? So doing work is just a measure of the result. Power is a measure of the efficiency of that work in at least one sense. There are several senses of efficiency, most of which are beyond the scope of this course, but you might get to study in some future coursework. All right. I'm going to actually just jump in here with an incredibly simple example. Let's do 300 joules of work in 0.30 seconds. Well, then the power would be 300 joules divided by 0.30 seconds. Which comes out at 1,000. Looks like I have two significant digits here, so that 0 is significant, the rest are not. And the units here would be joules per second. A joule itself is a kilogram meter squared per second squared. If we want joules per second, I guess all told that would be a kilogram meter squared per second, come on, second cubed. And again, alphabet soup of units. We are going to call this watts. The unit of watts is named after the Scottish physicist James Watt, who was instrumental in the invention of the steam engine. So the idea of power here as a way of classifying how a steam engine works was very important. Watt himself never used the unit of watts. In fact, the unit of meter wasn't popular at the time Watt was working. Instead, he worked with the unit he created called the horsepower. And so there's another place that we might as well go pretty early here. 1 horsepower is equivalent to moving 550 pounds a distance of 1 foot in a time of 1 second. So our force here is 550 pounds, which first requires us to remember that pound is a measure of force, not a measure of mass, right? Mass and weight are 2 different things. But we have a force of 550 pounds, and the conversion factor is that there are 4.45 newtons in 1 pound. Because this is a definition, I'm assuming that this 550 is an exact value, and of course the 1 down here is an exact value, but the 4.45 newtons is an approximate value, so we're going to round our result here to 3 significant digits, and it comes out at 2,450 newtons. Right. Next, our distance is 1 foot. Distances in feet make a lot more sense than forces in pounds, but still, we need this to be in metric units for how we generally work with things. So we need to know that the conversion here is that there are 0.305 meters in 1 foot. So our distance is 0.305 meters. And then our time is 1 second. The one bit of relief we have is that the US customary system and the metric system use the same units for time, so we don't have to do a conversion there. All right. And you probably have plenty of space to still work on your page, but I'm a little bit out of space, so I'm going to rewrite these where I have more space to continue working. Right. And then picking up from here. The work being done is the force times the distance, and power is work divided by time. We could do this in 2 steps, but I'm going to remind you that it's always possible to combine your equations first. So we have force times distance divided by time, just substituting in force and distance for work. Then from there, we can plug in our values. Our force is 2450 newtons. Our distance is 0.305 meters, and our time is 1 second. Remember again that the conversions were approximate values, so we have 3 significant figures here and 3 significant figures here, but the 1 second came from the definition of the horsepower, so we're treating that as an exact value. It's impossible to measure exactly 1 second, just like it's impossible to measure exactly 550 pounds, but the definition of the horsepower assumes that we can. All right, but plug this into the calculator, and it's telling me that the power that we get here is 747, right, Newton meters per second, which is joules per second, which is watts. All right, a lot of little things to think about here. First of all, unit conversions. I don't expect you to know the unit conversions between the US customary and metric system offhand, because there are so many of them and they're all ugly and stupid. So if one of those were to come up on an exam or something like that, I would provide the numerical value of it for you. Please don't waste time and energy trying to memorize it or fit it onto a reference sheet. Second thing, pay attention to the units as you're going through, pay attention to significant figures, pay attention to the way that the work and power formulas relate to each other. And then the last thing, let me come over here so I can fit everything onto the screen at the same time. This isn't the first time it has come up in this course, but please do pay attention to the fact that the W down here is watts, the unit of power. The W up there is work, a variable. We've used that already. We've dealt with mass, the variable m, and meters, m, the unit of distance. It's nothing new for us. It's something we know how to deal with. It's not going to make it any easier or harder, but it is something that's worth thinking about. The fact that these two ideas that use the same letter show up so often. In print, it's pretty easy to tell. Variables are always printed in italic font, and units of measure are always printed in upright Roman font. So if you're reading something, you can tell right away. I don't know about you, but I don't have a upright and italic handwritten font. I just have one way of writing the letters, so I can't tell in writing which one is which, but the context usually gives it away. If there are numbers in front of the letter, it's almost always a unit. All right. I've got one last example that I want to look at in this video. And it's the case that I kind of hinted at and then never did anything with, of what if we aren't actually pulling in the direction that we want to go? All right, so let's say we have a crate here, which is on the ground, and we are pulling on the crate using a rope that is pulled upward at a 30-degree angle. So the force is going upward, and the motion S is going straight across. That arrow doesn't look straight across. That arrow looks a lot closer to straight across. Right? Your force and your displacement are not in the same direction. Well, we've measured this 30 degrees with respect to the horizontal, sure, but the important thing is that that is the direction that we are moving. So this is, we'll call it F sub S, the S component of the force. And then I'll talk about this up here as F sub W, the wasted component of the force. Those things form a right triangle. And since this one down here is the one we care about, that's the adjacent leg of the triangle. And we get that Fs is F times the cosine of 30 degrees. All right, so only the component that is actually pulling in the direction of motion does work. The rest of it is wasted force. So why do I put the word wasted in quotes here? Well, there are a number of reasons that it might be necessary or at least helpful to have a force going in an odd direction. The first and most obvious is the practical consideration. Right? If I, a 6-foot tall person, am trying to drag a sled which is only 1 foot off of the ground, I'm not going to get onto my hands and knees and drag it so that I'm dragging parallel to the ground. I'm going to grab it at a convenient angle and pull it along with me. So just the fact that the force is going to come from my shoulder, which is 5 feet above the object that I'm grabbing, means that it's not going to be in a straight line. So there's a very practical reason that I have to do that. That said, it's not always a bad thing. The actual calculations are a little bit beyond what I want to get into in this course, but we know that the friction that an object encounters is proportional to the normal force acting on it, right? The amount of force that the ground itself has to pull up on the object so that gravity doesn't pull it down through to the center of the earth. If you are pulling the object up a little bit, that is going to reduce the normal force. And if it reduces the normal force, it's going to reduce the friction. So this is one that I come across a lot when my everyday life I'm trying to move a box out of the way in the basement to get to something that's stored behind it. I kind of lift up on the box a little bit as I drag it, which reduces the amount of contact that the box has with the ground, which reduces the friction, which makes it easier to drag. It takes less force to get the same amount of motion. So it is, in the very technical sense, a wasted effort, but sometimes it is necessary, sometimes it's even beneficial. With that, I think I'm going to wrap up. This video has gone on long enough, and there is enough here already without me trying to add any more to it. As always, thank you for joining me, and I'll see you in the next video.